All right, so today we're going to talk about random variables. And Jaden, you inspired me to bring a grid on my notes. It's not going to help my penmanship, but it will help how straight things are. Good morning, Ryan. Today we're talking about random variables and their distributions. So first we're going to define and describe discrete and continuous random variables. We kind of know that already, but we'll talk about their distributions. RVs, random variables, and their distributions. So we'll be talking about, I'll define these later, but PDFs, probability density functions, and CDFs, cumulative density functions. And then we're going to calculate probabilities. Of events based on these distributions. And we're going to do this graphically. And we're going to do it with calculus. Very basic calculus. Do not worry. I don't know about that. I think everything's proper in this class. I don't mess around with improper stuff. Okay, so I'm just going to jump in. We know what discrete variables are, right? Number of cars that pass through an intersection in an hour, the number of cloudy days in a week, binary outcomes, is it snowing, is it not snowing, that sort of thing. And what we'll use is, obviously we have to map that to numbers, right? Binary outcome would be 0 or 1. Number of cars, that's pretty easy. Number of cloudy days in a week. And so we're first going to start with our discrete random variables. And we'll say X is an RV, a random variable. And this is just some particular outcome. And so big X, and so we'll call this big X. Big X can represent the, so when we say it's a random variable, it represents all of the potential outcomes. So big X represents all the potential outcomes. And we'll stick with that kind of number of cars. So number of cars passing through an intersection. And then what we're interested in is then saying, okay, what's the probability that big X is equal to some outcome, little x. So little x, this is the random variable, it's all outcomes. And little x is a particular outcome. And we can write this as, we'll kind of introduce this nomenclature, but it's P big X of little x is what we call the probability mass function. Or PMF. And this is where we're going to be talking about the actual distribution of a random variable. So we can write this out graphically. It's kind of the best way to do it for a discrete variable. And this is x, and this is P of x, P big X of x, also known as our PMF. And we can give these values. These are relative frequency values. And then the number of cars that pass through an intersection. Well, these are all the potential values that big X can take. Call that big X. So it can be 0 cars, 1 car, 2 cars, 3 cars, etc. And then we'll go out, you guys will actually do this for a homework assignment. We'll go out and we will collect some data. Say we sit out there for 20 minutes. How many cars pass through the intersection on a light cycle or something like that? Traffic light cycle. And then we crunch those numbers and we come up with a relative frequency. So this is just, we'll say Ni over N, right? So the number of observations with a particular value of X over the total number of observations. And we'll plot that. So we get this, we get this. Okay, and we have at most, we have 5, and then we don't have 6 cars in our data set. So now we can ask ourselves, okay, what's the probability that some outcomes happen? So 0, so X is greater than or equal to 0 and less than or equal to 2. And then we can use our nomenclature. I said it's not going away, but we're not going to be dealing with it so much directly. So this is probably that X is equal to 0, or X is equal to 1, or X is equal to 2. And are these mutually exclusive outcomes? Yeah, so if we do or, then we don't have to subtract the intersection, right? Because they don't intersect. So then we can just say this is a probability X is equal to 0, plus probabilities that X is equal to 1, plus the probability that X is equal to 2, because they are mutually exclusive. No intersection. So we're not going to subtract out that intersection. And then let's go ahead and add this up. That's pretty easy, right? So we can then, okay, so we'll do one more intermediate step. So this is just kind of generic probabilities. Well, to solve for this and to find the value, we go back to this PMF, this probability mass function. And so we say this is the probability, and this is our PMF right here. So we're just plugging that value into this function. And it's really just a kind of a graphical function, right? We'll actually do discrete variables, and this will be a real equation that we'll use. But we go to the PMF, we say we plug in 0, so X equals 0. The PMF gives us 0.1 plus 0.2 plus 0.3. So finally, we sum those up and we get 0.6 is the probability that X has those values. Okay, so that's a probability mass function. It's based on discrete data. We draw these little lines based on data, or there could be some theoretical values for those. And that's how we use it. We just plug our X values in, we find our Y values, and we can add things up. And that gives us the total probability. Now, why do we call it mass? Probability mass. It's really just an arbitrary way of talking about it. Well, not totally arbitrary, but we'll say if probability is mass, mass is kind of like this fundamental unit of matter, then we can just add things up. We can say, we'll take the probability mass of this and the probability mass of this, and we'll add it up. So the units of PMF, so the Y units, right, are mass or probability mass. And this, we're going to set it there, and then we're going to return to this when we talk about probability density, which is a little more kind of the next level for continuous variables. And we'll talk about why density relates back to mass with some math. Okay, so here's our PMF. Now let's go to what's known as a cumulative distribution function. And basically throughout the rest of the semester, we're going to be going back and forth between PMFs and CDFs, or PDFs and CDFs. And we'll write out, first we'll do the kind of symbology. We'll say the probability that big X is greater than or equal to little x. And here's how we're going to write it, is big F of X given little x, or as a function of little x. So this is a capital F. And we can put in a value here. So what's the probability that big X, that the random variable takes on some value that is less than or equal to 2? That's a big X. Let's see, so less than or equal to, okay, yeah. Okay, so cumulative distribution function gives you the value that is less than or equal to. And then we can write this as probability that X is equal to 2, or probability, or X is equal to 1, or X is equal to 2. So it's just the same thing that we did before. And we know that if we want to find this, then we just add these up. But that's the same thing you would do with a cumulative distribution function. So this gives you that directly. This is the formula or the function that gives you that summing the probabilities up to a particular value. So this is equal to big F of X, our random variable, by plugging in 2, which we already solved. So what we can say is that big F of X, capital F of X, of some little x value, some outcome of that random variable big X, is equal to summing up the probability mass function and let me just give us a little more room there so we can write out a little better here. Oh, didn't give us everything. Okay, so, and this is for all the way to n. So whatever that value is, right? All we're doing, so with this cumulative distribution function, all we're saying is you sum up the individual values up to that value. So a cumulative sum. And we can draw this out. So for a discrete variable, we have to draw out the cumulative distribution function. So we have x again on this, we have 0. I'm going to put 0 all the way over here. So big F of x is on the y-axis. And notice that we go up to 1, right? Because if you sum up all those probabilities from before, you go up to 1. And then we'll write this out. So we start at 0. The 0 observation happens 1% of the time, or sorry, 10% of the time. So we start out there. I'll just draw it in a different color. So at 0, we're already at 0.1. We come across, we get to 1, and then it's a stair step function. There's an open circle, so we don't include that. It's basically you have a 10% chance of being 0 all the way up to, but not including 1. And then 1 jumps us up to 0.3. Then we come across to 2, and then 2 jumps us up to 0.6. Sorry, right here. 2. We come over to 3. 3 jumps us up to, looks like there's another 0.2. Let me just go back up here. 3 gives us another 0.2, so that gets us up to 0.8. And then we have some 0.1s. All the way up to 1. But we didn't see any 6s, so we'll keep an open circle there. And this just means kind of up to, but not including. Because we can't have 1.5 cars or 5.5 cars, right? So just some notes about CDF. So this is our CDF, cumulative distribution function. And CDFs increase monotonically. Does anyone know what that means, monotonically? It doesn't go back down. You're always going in one direction. So you're just going up the stairs. You're not going back down the stairs. Because as you go across the different options for X, the different potential outcomes, you're just adding whatever incremental probability you pick up along the way. So you're not going back down. So they always go from 0 to 1, 0 probability at one end, 100% at the other end, and then we increase monotonically. And then CDFs always converge to 1. Monotonically. And then we can just kind of, make this a little more broad. So for our random variable X, that is between -infinity and infinity. If we plug in infinity into that formula, then we're going to get 1. So basically, and this makes more sense when you look at continuous functions. Eventually, you're going to get 1 at the end, the most extreme value of X. In this case, X only went up to 5, I think. Okay, so that is the distributions for discrete variables. Let's jump into um, continuous variables. What are some examples of continuous variables again? Wind speed. How about the, I was watching Super G last night on the Olympics, and the time of it takes for a ski racer to make it down the hill. It was 1 minute and 13, 0.58 seconds was the first place. And then everyone else comes down. I think the first place person's like in the early heat that goes, and then everyone else goes, and then all their times are some continuous variable of time that it takes to get down, right? So time. How about our folks on Zoom? What's another continuous variable that's near and dear to your heart?
Snowfall.
Snowfall, so like snow depth, right? How much snow fell? So just to kind of summarize this, we can take on any value between negative infinity to infinity, theoretically speaking. And the challenging thing is, what's the probability for a continuous variable? What's the probability that x equals some particular value of x? That you're going to hit, and if you think about it, you have to define it as say it's just what's the probability that we get 1 inch of snow? So that's 1.00000000, right? So this ends up being 0. We can't, the probability of actually equaling something is 0. And so x can take on any number of values. There's infinite possibilities. Therefore, we have to, we must evaluate continuous random variables within intervals, aka histograms. And this is lab 1. We're dealing with histograms, and I give you continuous random variable rainfall depth, and you're going to use histograms to describe the distribution of it. So here's a histogram. We have x on the x-axis, so all the values that we could have of random variables. And then on the y-axis, we're going to introduce this. And so this is, we'll introduce it and then we'll define it a little bit better. So little f of x given x, or evaluated at x, also known as our probability density function. So density. And then we're going to evaluate what we're going to call the probability density function, or PDF, of daily water demands in million gallons per day for the city of Grand Junction. I don't know if this is true or not, but I'm just going to make some numbers up. So here's our x values. And then here are so these are bins, right? Or intervals. And any particular day, maybe we have 0.237 million gallons per day, right? So all these numbers can vary. So we'll start off with 0 to 0.5 as this is our probability density value. We'll go up to 0.2. 1.5. And then I think this is 0.5 and then 0.25. Okay. So here's our histogram. So X has units of million gallons per day. Million gallons per day. MGD. So some things about the histogram that we want to know. We have a bin width, which is uniform typically. They don't always have to be, but for this class, we'll just use a uniform bin width, so delta X. And then here's how the math plays out for this. So we can't evaluate the probability that X equals some value for a continuous interval or for a continuous variable. So we can evaluate the probability that X is in between some particular values. And so I'm going to say greater than 0 and less than or equal to 0.5. Now, can we just read off of this graph and tell the probability? You don't really know the answer to that, but the way density works is that you can't. This is not, if this were frequency, and you can make a histogram where you have frequency on the y-axis, so 0.1, which would be like 10% of the observations fall in that bin width. You can make a histogram like that, but that's not how I've set it up. And in the lab, you're actually going to convert between frequency and probability density. So to do this, we take the probability density. So we take little f of x evaluated at 0.5 or for that bin. So 0.5, 0 to 0.5. And then we multiply it by delta x. So there's this range, and we multiply it by the bin width. So this is equal to 0.1. So that's that value right here in the probability density times our delta x, which is 0.5. So the probability then becomes 0.05. That's our probability. And we can go and do that for all of these. And hopefully, I don't know if I wrote it up correctly, but a real probability density function, if you do that, basically delta x times the density value within that bin, everything should sum up to 1. So let's just take out a little kind of calculus theorem right here. So if we evaluate the midpoints, if we evaluate f of x at the midpoints, actually, let me just write it that way. Then we can say the probability that x minus delta x over 2. So this would be, so here is So if we're interested in some value of x, we're going to evaluate it at the midpoint. So say it's just 1. So say x equals 1, we're going to say delta x minus over 2, so half the bin width over this way, right? X plus delta x over 2, so half the bin width this way, is equal to evaluating that PDF at x times delta x. That's essentially what we did right here. We just said, okay, we're interested in what's the probability that x takes on some value between these two bins. That's just equal to the probability density function between these two bins times the bin width. So all we did is just kind of move over to this point right here. And then we're going to look halfway this way and halfway this way. Okay, so then we can say as delta x goes to 0, we go from approximate values, right? Because the bin width is really just based on, it's an arbitrary thing. You can make those bin widths smaller and smaller. We go from approximate values to exact values, assuming we have enough data to fill that in. And so we can say that our PDF, f of x is f sub x of x, is equal to the limits as delta x goes to 0. All over delta x. And this equals our PDF, our function. So we're basically saying we can take that bin interval and make it infinitesimally small, and then that will give us our probability value evaluated at a particular location. This brings us to continuous variables and just actually looking at functions. So probabilities, distributions that are functions. So let's look at just how this plays out. Okay, so we're gonna just do a simple triangular function here. And it peaks at 2, just a symmetrical function, which takes on a probability density value of 0.5. We go down to 4. And we will define this function mathematically. So the probability density function is equal to x over 4 between 0 and 2. So not including 0, but right up to 0, and then including 2. And then it's equal to 1 minus x over 4 for 2 all the way up to 4. So it's just a 2-part function. And so if we kind of go back to this, this limit right here, this is the definition of an integral, which tells us that the probability of x being between two values. So we'll just say A is equal to the integral from A to B of our probability density function times that differential distance. So you're going to be doing a lot of these integrals. We're saying if we're interested in finding the probability of X taking on some values or being within some range, then all we're going to do is integrate that probability density function with respect to X. So back to this example, if we want to say what's the probability that X is between 1 and 2, then we use that integral. We just say, okay, well, let's integrate our function from 1 to 2. And we look at our function, okay, from 1 to 2, this is the one we're going to use. So it's just X over 4 dx. So we get 1/2, if we integrate that, we get 1/2 X squared over 4 evaluated from 1 to 2. And then just plug those numbers in. And then we get 3/8 or 0.375. So now you could do this. Let's see how much time we have. Yeah, why not? So you could do this, and let's go ahead and say, what's the probability that X is between 0 and 4? And go ahead and do that problem and see what the values come out to be. I mean, for the purposes, I mean, to be, yeah, it's not going to be actually 0, but you plug in 0 and 1. So you're going to put this integral with all these parts. So you can do 0 to 2 for this, and then you can do 2 to 4 to this. So no surprise. The first one is 1/2. And the second one is 4 minus 1/2, 16 over 4 4 minus 2, right? So 4 minus 2 minus, and then this is 0, right? 2 minus, no, that's just 4/4. 2 minus 1. So minus 1. So that should be 0, or is that plus? Wait, did I do something wrong here? Should be 1/2, right? Doing math on the fly. So this is 4 times 1/2, which is 2. So 4 minus 2 is 2. And then -3/2. Okay, so 2 minus 3/2. Okay, so 2 minus 3/2 should give us 1/2. And then we get 1. So what we're doing here then is just by integrating this function to calculate the probability, it's the area under the curve. Does that make sense? And that's all we did with the histogram. We're calculating the area under that histogram to give you the probability. And how that translates to density is if you, so let's just go back to density. So with probability density is if we integrate density, over a volume. So we take density, which is mass over volume. And if we integrate that over some volume, then what do we end up with? You end up with mass. So we take the density of something, we integrate it over the volume, you end up with that mass. And so this is kind of the analogy that if you integrate over the probability density function, you end up with essentially probability or probability mass. Not the best analogy, but that's kind of what's behind it. We've got 5 more minutes, so let's define the cumulative distribution function. For continuous variables. So instead of summing probabilities, like we did with the PMF, now we're summing areas. Within that PDF to get to the CDF, right? So we're summing essentially f x of x delta x, or dx. So for a histogram, if we sum up all of the, sorry, that's a little x, little f. If we sum up all the areas under that histogram, assuming they have probability density values, we multiply it by the bin width, we get 1. But for a PDF, a continuous distribution function, we're integrating. And we just demonstrated that with the triangle. So we're going to define then the CDF as big F of X as before. And that's just the integral from 0 to X, whatever that value is that we're plugging in there, of our PDF. So if I want to know what's the probability for this function that we had up here, that X is less than or equal to 2, then I integrate it up to 2, and we got that area of 1/2. And so we can write this out as the probability that X is less than or equal to some value of X. So big X and then little x. And then we'll draw it out for that triangle function. And we had values of 1, 2, 3, and 4. And then as before, it sums up to 1. So all we're doing is accumulating area. So we get to 1, I think we're about 0.25. We got up to 0.5, so half of that area. 3.75, and then 4, 1. And this is a continuous function because we defined it continuously. And if we just want to read off a value, so we say, what is big F of X, the cumulative distribution function at 2? This is equal to the probability that X is less than or equal to 2. And all we do is just read off of this value. It's the same as going up to that triangle and integrating and calculating the area up to that point. Okay, so I'm going to post on Canvas just some examples, some more examples of this and how it plays out with different kinds of functions. So you have those to refer to. All right. So look for those by Monday.
You scroll up.